So let's have a look at the manipulators, and the manipulators within a particle system, they are local to this particle system only. There are global manipulators, which is created on the playground manager. I could show you how this kind of works differently for when using local or global. Let's create a new particle manipulator here, and immediately you'll see that it starts to affect the particles. The first setting for a manipulator is the default setting is the attractor, which just attracts particles. And depending on the shape of the manipulator and the size of the manipulator, it will affect particles within range differently. So let's change the shape here to a box instead, and the box is set up by a rect with bounds, which you can drag directly in the scene view here. And that is how you specify the size for this box. It also takes rotation into account. Let's go back to a sphere. And if we were to increase the strength of the manipulator, you'll see that it starts to draw particles towards the manipulator a bit more rapidly. And the smoothing effect and distance effect here will determine how the strength is applied over the size of the manipulator, or the distance. So the smoothing effect will add a bit of smoothness to the strength value, and the distance effect will determine how strong this effect is, depending on how far away the manipulator is. So this is more basically for tweaking the manipulator, how it should act. And you'll also see something called lifetime filter here, where we can filter out particles by their lifetime. So for example, we could like release those later or earlier. And this is done by a normalized value from 0 to 1, where 1 means the full lifetime of the particle. And these are available for all the kind of types. I'll show you those in a bit. So the particle filter, this setting will filter out particles from the particle array, where it will only do a certain amount of particles, as you can see. Let's disable that, and then we can inverse the effect as well. So currently the manipulator and the particle system, they are within range, but if I were to drag the manipulator outside of the particle system, or the particle system outside of the manipulator's bounding box or area, you'll see that it will just stop affecting once it enters the manipulator's area here. Let's change that again to and something like that. You also have this attractor gravitational feature, which will add a bit of, it will still attract particles, but will be more of a slingshot effect to them. And I believe we could try something sort of, you can see that it sort of has this slack to it. So this would be efficient to use if you kind of have this some sort of space effect or something where you kind of want to simulate a particle slingshotting through the gravity of a planet or something like that. Now let's set the values back, and then we have a thing called repellant, which will repel particles whenever the particles enter the area of the manipulator. And there's this thing called, or let's have a look at the vortex first, because this is one of, oh yeah, the strength was a bit too heavy there. But what this does is it creates this vortex swirl effect around the transform axis for the manipulator. Perhaps we need a bit more lifetime to the particles, just to show you. Yeah, so it obviously needs a bit of tweaking to behave the way you want. So let's have a look here at the property manipulator, and the property types are quite many. You can change the color within range. Let's do something which is noticeable. So we can change the colors of the particles that is entering the manipulator's area. Let me just set the rotation back. And you can do this with a transition as well. So it will linearly interpolate, and you can disable only color in range to get the effect to keep on going when the particle exits the manipulator as well. And keep color alphas will remember the particle's alpha when it is inside the manipulator, otherwise the alpha from the specified color will be used. So that's the color property. You can also affect the velocity. For example, let's set that to 10. So you can get this kind of control behavior of where a particle should start to go in a certain direction. And if we set the transition was set to lerp there. If we set it to none, we get this immediate effect. Additive velocity will keep on adding, and this is basically the same as doing a transition for the normal velocity property there. Then we can change size, and that would be the size that is specified here by particle size. So whenever the particle enters the manipulator, it will get the new size property. And you could set that to only size within range as well. And of course transition that effect. So let's do a bit bigger there. And the strength will have effect there for how fast the linear interpolation is moving towards the final particle size value. And then you can specify targets for your particles by transforms. So a default, you will have the manipulator itself, the transform of it. And this could be a list of several. So let's create a new game object there and assign that to the second target. Let's see, where did that end up actually? Let's increase particle count. And as the manipulator isn't big enough, there we go. And here you have something called zero velocity strength, which determines how much should velocity be zeroed out over time when a particle is inside this sort of manipulator. So that's the target. Then we have this thing called death, and this will make the particle die sooner. So this can be used if you kind of want to restrain particles. You don't want them to enter certain areas. And this could be done with a transition as well to make them die a bit later, but still earlier than their specified normal lifetime here. And then the property types can have the main types here as well. So this attractor is the same as this attractor. Why this is layouted like this is because you can have combined manipulators, and I'll cover that in a bit. So let's move on to well, we have lifetime color, and here you specify a new lifetime color for your particles. Let's see how that works. So let's do something like that, red and blue. And set that to none. So all particles entering this manipulator, they are white from the beginning, and then when they enter, they get this new lifetime color set. And then we have the mesh target, which is a mesh specified within the scene. Basically, this is a world object, behaves the same, just reversed from emitting from as a source. You'll instead target the vertices, which could be really efficient. And you also can do that with a skin mesh. And you have this turbulence manipulator as well. If you only want turbulence inside a specified area, you could use this, which opens up for quite cool behaviors. Right, and you have the simplex and Perlin algorithm there. Also, what's good to know about the turbulence manipulator is that it will have different strengths to it depending on how smoothing and distance is set. So this is what sort of makes it a bit more different than from the forces, using forces turbulence. And then we can have a state target to target pixels within the scene. So same thing there, it is a reversed effect from using it as a source. And then we can target splines as well. We could try that out just quickly. Let's have a look at how that works. You'll see that we have we get all particles set to the spline immediately, and that is because we don't have any transition. Should we enable that, we will see that kind of effect moving from the particle system itself and towards this playground spline. And let's see, we have this thing called target method here. You can either use the spline time or the particle time for setting the positioning here. So the spline time, the particles will try to look for the appropriate time in the spline. If we're using particle time, it will match up with where the particles are in their current time, in their lifetime. So that is the spline target. We also have this moth manipulator, where you can apply new properties. You see that here it's sort of pulsates from small size to large size. The particle property here is set to size, and the type is a sine wave. Applying this, where the value is determining how big the particle will be, and the rate here is how fast the sine wave will move through this property. So I just increased the rate here to 5 to get a more faster pulsating effect. And you can clamp this value as well. You can clamp the in value, which basically is the value for the particles before they enter this property or is calculated by this property. Or you could clamp the out value, which is the returning value for when the manipulator has calculated the new size or new value for the particle property. So let's say a particle cannot be smaller than 0.1 and then it cannot be bigger than 0.5. So you start to see this kind of clamped effect there. Sine and cosine, they are very similar, but you can put several of these onto one manipulator or several manipulators to have them cooperate to create circular patterns or something like that. You also have linear interpolation here, which let's see, and this is controlled by the value. And you'll also find adding. So this effect is a bit big at the moment, and the rate here will be the in coordination with the value here. When adding and subtracting, obviously the particles will just inverse, so we kind of see the same effect here when we add and subtract. You can also do rotation using this, and you can set velocity using this. So if we were to, for instance, sine wave this, you can see that it starts to, it goes through this sine wave algorithm to apply velocities. And the rate here and value is done by vector 3 values when we're using velocity. Same thing goes for position. So this can be used to kind of really add quite interesting effects to your particles within specified areas. So that's the math manipulator. And we have this thing called combined manipulators as well, where you can combine several of these. For instance, apply a color. We could also create another one. And let's do a math manipulator with, let's try the position using, could have a bit more rate there, not as much on the y axis. And let's create another one which also is set to math and position. Let's do a cosine there. Let's set those values to 0 on the y-axis and have 0.5 on the x-axis value and 5 on the rate there. So you start to see what I meant by combining sine and cosine here to kind of create circular patterns, which could be useful. And this is a bit more optimized than using several manipulators when you combine them, because you only have to check for particle distance once within the manipulator. So that is the different types. You can also have events on your manipulators where you can track particles. And the tracking method determines how particles are tracked. Manipulator ID is the fastest, where the ID set to each particle of the current manipulator will be checked for. Using particle ID is a lot slower. You'll see that the effect starts to, it can't cope really with all these particles, because this is starting to compare the particles if they are the same ID as the current available particles within the manipulator. So try to use manipulator ID if that works for you, or if you have fewer particles where you have a lot of manipulators affecting them. If they are overlapping, for example, then you might have to use particle ID to get the exact particle ID from the specified manipulator. And the events here, they will send, whenever a particle enters or exits the manipulator area, it will send an event through script, which you can listen to through an event listener. You can also send the birth and death and collision event within this, within the range of the manipulator. So let's talk about the differences between a local manipulator on a particle playground system and a global manipulator, which is affecting several particle systems. As you've seen how local manipulators work, they will only be exclusive for the particle system you're currently setting the manipulator up for. The global manipulators, they have the same features, but they will affect several particle systems at the same time. So let's have a look at how that actually works. Let's duplicate this particle playground system and sort of set them up like that. And using this global manipulator I just created, which is set to attractor, so we can expect that particles should start to attract towards this. Let's increase manipulator strength, and you'll see that the manipulator is affecting both particle systems at the same time. And you can specify which layers should be affected. So keep in mind that if you have certain particle effects which shouldn't be inside or isn't affected at all by a certain manipulator, set the particle systems which should be affected to its own layer here. And that is just for optimization reasons. So the global manipulator won't look for particles inside any sort of static particle effect, which shouldn't be involved in this at all. So that is the differences. Just go crazy with the manipulators and try these features out. That's the best way to learn how they kind of act in the scene, and every scene is different. I hope you've enjoyed this video, and yeah, just have fun. Okay, thanks for watching.